Okay, so today we're going to do the oscilloscope experiment. So here's the oscilloscope right here. This is what the oscilloscope device looks like. Some of this video is going to be a little shaky. The picture will shake a good bit. So just apologize in advance for that, but it's the best way I think to show you what's going on. So here's the oscilloscope. So what does an oscilloscope do? Well, it's basically like a voltmeter. You measure voltage and it connects like a voltmeter. You go parallel to whatever you want to know the voltage of, okay? So outside your main loop of circuit. But instead of just giving you one numerical value like a voltmeter or a multimeter does, it's going to show you a picture. It's going to show you a plot of voltage as a function of time, okay? Now let me zoom in closer to the screen with this on the oscilloscope. Hopefully you can see now. You see that there's a grid, okay? So there's this grid. What this grid means is the x-axis is actually showing you time, okay? And the y-axis is going to be voltage. All right, so you're looking at a graph of voltage versus time. Right now it's not connected to anything, so it's just zero. But anyway, normally you would look at a graph of voltage versus time is what it would normally be showing you. And you'll notice down here, like say, notice where this says 500 millivolts. That's telling you that each block represents 500 millivolts. Over here, 250 microseconds. Right now, each block horizontally represents 250 microseconds. Okay. So right now we're not connected to anything, but let me show you one other piece of equipment here. Okay, this is the function generator. So it's your power supply in this experiment. But one thing that's different from other power supplies we use is it puts out AC voltage, which means voltage that changes in time. So the most familiar example of that would be a sine wave voltage, like what comes out of the wall outlet, just any ordinary household wall outlet. It puts out a sine wave voltage at 60 cycles per second and about 110 volts at the peak. All right. So this function generator can also put out a sine wave voltage and some other kinds as well. And you can change, this number is actually the frequency. You can change the frequency as well as the amount of voltage, okay? So anyway, okay. So let's say I take my cable that's coming from my scope and I connect it to the function generator, all right? So let's connect it. Now what I'll see on the screen is a sine wave. So that's showing me, that's plotting the voltage for me that's coming out of the function generator. And I can make measurements, okay? I could measure, for example, the height of the sine wave. Right now I could say it's it looks like about 3 centimeters tall, a little bit more than that. And each one represents 500 millivolts, so I could figure out what my peak-to-peak voltage is, okay? If I want to know the period of one cycle of this, then I could count, for one sine wave, ever how many blocks that is, ever how many centimeter blocks, and then that will be multiplied by the 250 microseconds because each block represents that much time, okay? So when you make measurements with this, you'll be measuring things in centimeters, just like a ruler, just like we did in 210 a lot of the time. So these blocks are centimeters, both up and down, both vertically and horizontally. And you could have an uncertainty for it that would be just like when you read a ruler or a meter stick when you're making measurements like that. So you could say plus or minus 0.1 centimeter because that's half of the smallest little small division there, okay? All right, so, and then you can use that and multiply by your scale and you get the uncertainty in the voltage as well as the actual centimeter size, all right? Okay, now let me back off a little bit and So there are a lot of buttons and knobs with the oscilloscope, and that probably looks a little bit intimidating, but there's really only 2 or 3 that you'll have to use as far as today is concerned anyway. So there are these 3 big knobs right across the front. You'll see voltage per division, volts per division, and seconds per division. They basically change the scale of the plot. That's just like when you're drawing a graph on graph paper and you always have to decide, I'm going to make 1 centimeter represent 1 volt or 2 volts or 5 volts or 5 seconds or 3 centimeters or whatever. So whenever you're doing a graph on graph paper, you always have to decide on a scale. You pick a scale that optimizes it. So that's what you're doing here. And you could change this, like say, right now, I could make the sine wave bigger if I wanted to. Well, okay, I made it smaller. I can make it bigger, all right. I can make it smaller, all right. The most accurate measurement would be if you take up as much room as you can, but without overdoing it, okay. Same way with the horizontal scale, with the time scale, okay. So I can pick whatever scale I want, and that's what those 3 knobs there do, okay. The position knobs right there, they just move your signal around, okay. So when you're trying to make a measurement, you might find it convenient to say maybe, let's say if you wanted to put a peak right on a corner of the grid, and that way it's easier to count off and easier to do a measurement that way. So you can orient the signal wherever you want to. Now let me emphasize, none of this is changing the physical voltage that comes out of the generator. It's just a matter of how the scope represents it as far as its scale and where it puts the signal on its grid. Okay, so that's mostly what you have to do with the scope. Maybe 1 or 2 other things that the instructions will tell you about. Okay. All right. Now, a couple of other pieces of equipment that are not familiar to you, possibly. Okay, this guy here, this big red thing, that's the inductor. All right. It's just a coil of wire, okay? You see the loops of wire there. It's just a coil of a whole bunch of loops of wire, all right? Some of you will have one that's actually kind of copper colored instead of red, but anyway, it does the same thing. We don't really have to get into too much today what it actually does. It has to do with magnetic fields and so on, but we're just going to put it in a circuit and make some measurements with it. You might have noticed already that there are 2 cables that come out of this oscilloscope. So one of them is what we've been using so far, and there's a second one. If you wanted to look at 2 signals from 2 different sources at the same time, you could do that. All right, so and we will do that when we get to the part of the experiment that uses the inductor. All right. Okay, so one more component that will be new to you, or at least to a lot of you, is this, the diode. The diode is just that little tiny semiconductor part, and then you've got the wooden block that it's mounted onto. So it's going to tell you to take the diode and put it in a circuit, and you'll see it change the display on the oscilloscope screen, and you will figure out from that what the diode is doing, what's its electrical function. Okay, some of you I'm sure already know, but anyway, it's going to ask you to figure it out just based on what you see it do on the oscilloscope screen. Okay, so that's the experiment. It's an in-class, and so you'll be done with it when you're done with lab today. There's no report on it. Okay, so now the lab midterm exam that most of you took last week, they've been graded, but there were several people who were unable to take it because of being quarantined or whatever. So I'm not going to talk much about it until everybody has had a chance to take it. I will say that quite a few people actually did rather well on it, and then some people didn't do quite as well. So anyway, that's pretty much what I can tell you right now. So, okay, I'll just leave you to work on the experiment.